Welcome to NPTEL online certification course on aero engine gas turbine cycles, lecture 17. In last lecture we started doing the parameter calculation for actual gas turbine cycle for two spool configuration. Then we have done our cycle analysis for the given information. So at the end we have done the calculation for the exit velocity, and now today we will be discussing further the next parameter calculation. So let us see what all information we are having. So this is regarding two spool turbojet engine, and we are doing calculation for the ground condition. For ground condition our Mach number is 0 and condition for the temperature and pressure are 288.15 Kelvin and 101.325 kilopascal. And for this turbine entry temperature, that is what is 1200 K. Now let us move towards the next. See, we have done our calculation for the exit of intake. That is what will be the input parameter for LP compressor, and we have done the calculation for exit pressure and temperature of LP compressor. This information we have transferred to HP compressor, where we have done our calculation for exit pressure and temperature of HP compressor. Then we have taken combustion chamber, and for this combustion chamber we are given with the information of pressure drop. We know what is a maximum turbine entry temperature, and based on that we have done the calculation for outlet pressure and fuel air ratio. Now with this information we have done our calculation for the HP turbine, the exit condition of HP turbine, that is T06 and P06 we have done calculation. This information further been transferred to LP turbine, where we have done our calculation for exit pressure and temperature. My LP turbine exit and nozzle, they are connected with the tailpipe, and for that pressure drop it is given. That is what will be giving us say pressure and temperature at the exit of the tailpipe. Now for the nozzle we have done our calculation for the critical pressure, and based on that calculation we have realized our nozzle, that is what is choke nozzle, and based on that we have done our calculation for the exit static pressure, exit static temperature and our exit velocity. Now let us move forward for say performance parameter calculation. So performance parameter, as we have discussed, they are mainly thrust specific fuel consumption, fuel air ratio, propulsive efficiency, thermal efficiency, overall efficiency. This is what we are doing for two spool configuration. Now for the two spool configuration, this performance parameter, they are mainly been affected by overall pressure ratio or compressor pressure ratio. The difference compared to single spool configuration is here we are having high pressure compressor pressure ratio and low pressure compressor pressure ratio. So overall pressure ratio that we can write down, it is LPC pressure ratio into HPC pressure ratio. Be careful, this pressure it is in multiplication, this is not the addition of the pressure. Okay. Then we have our next parameter, that is what is turbine entry temperature. We have say component efficiencies, maybe we have the flight condition. For this configuration we have taken say ground condition, so flight condition will not come, flight altitude also will not come. So mainly if you look at, we will be doing our calculation for the ground condition considering the parameters like overall pressure ratio and turbine entry temperature, and what will be the effect of these parameters on the performance of the engine. So let us begin with the calculation. So very first parameter we will be calculating, it is thrust. So thrust, that is given by say m infinity into 1 plus f V9 minus V infinity, this is P9 minus P infinity into area. So if we look at these parameters, this f fuel air ratio, it is known to us, V9 we have calculated, V infinity, that is what is 0 because it is a ground condition. Now here in this case, since my nozzle is a choke nozzle, that is the reason why we know this P9 minus P infinity, but the unknown parameter for us, it is area. Now in order to calculate that area, we will be using our fundamental equation. This fundamental equation, it is say my continuity equation. It says my mass flow rate at the exit, that is what is given by density into area into velocity. Now, this mass flow rate what we have, that we will be writing as m infinity plus mf, or we can say we will be taking m infinity common, it is m infinity into 1 plus f. Now, V9 value is also known to me, but a known parameter here is my density, static density at the exit. If you recall this density, we have calculated our static pressure and static temperature. So, let us put that. It says my density, it is given by P9 by RT9. Now, this pressure value at the exit, it is known to us. R we are taking 287 and T9 we have calculated it is 693.39. If you will be putting these numbers, my density is coming as 0.6122 kg per meter cube. Now, based on that we can do our calculation for the exit area, and this exit area is coming 0.6074 meter square. Now, once this area we have calculated, we can calculate what will be the radius of the nozzle exit. So, that we can do the calculation. Here in this case, we will see my thrust, that is what we are writing as say m infinity, it is given 186 kg per second. F value is also known to us. This V9 we have calculated, since my ground condition we have, so V infinity is 0. This nozzle is a choked nozzle, and that is the reason why we are taking our P9 equal to critical pressure, that is what is say 121.83 kilopascal. So, if we will be putting all this together, it is giving me the thrust as 108.65 kilonewton. So, this is the thrust at the ground condition. Okay. Now, the next parameter what we have is thrust specific fuel consumption. This thrust specific fuel consumption, it is given by m dot f divided by T. This m dot f value we can write down as f into m infinity, since we have done our calculation for f and we know what is our thrust now. So, based on that it says this thrust specific fuel consumption is coming 0.0288 gram per Newton second. So, this is our next parameter we can say is a thrust specific fuel consumption. Now, our required parameter of interest being an engineer is it's in terms of efficiency. So, let us do the calculation for the efficiency. Very first, that is what we are writing as a propulsive efficiency, that is given by T into V infinity divided by T into V infinity plus this as a change of kinetic energy. Here in this case my V infinity, that is what is 0, that is why my propulsive efficiency is coming to be 0. Let us calculate the thermal efficiency. In thermal efficiency also, if we look at, this is my denominator term of propulsive efficiency divided by amount of heat we are inputting. Since my V infinity that is coming 0, we will be putting this number and it says the thermal efficiency is coming as 17.4%. Now, major interest for all of us, it is overall efficiency. So, this overall efficiency we are writing as propulsive efficiency into thermal efficiency. Here in this case, if we look at, since my propulsive efficiency is 0, so my overall efficiency will be coming as 0. Okay. Now, let us try to understand the effect of change of parameters what we have. So, here in this case it says my V infinity is 0 kilometers per hour, P infinity and T infinity they are atmospheric condition. We have done our calculation for the exit area, we have done our calculation for net thrust, thrust specific fuel consumption and thermal efficiency. Now, let us take first parametric study. Here in this case, the parametric study what we are selecting is effect of LP compressor pressure ratio. We will be putting HP compressor pressure ratio constant and turbine entry temperature to be constant. So, basically if you recall, for the single spool configuration, what we have done is we have studied the effect of change of pressure ratio putting turbine entry temperature constant. Since here we are having two compressors, LP compressor and HP compressor, so let us try to understand the effect of change of pressure ratio of individual compressor. So, very first parameter we are taking, say here in this case, this x axis, that is what is representing my LP compressor pressure ratio, this y axis which is representing my thrust, and because of variation of LP pressure ratio, say my HP pressure ratio we have kept constant. So, overall pressure ratio we are varying by varying the LP compressor pressure ratio. So, this axis is representing overall pressure ratio. So, if we look at here, this is what is our design condition we can say. Now, let us try to realize, let us try to understand this curve. What it says, if I am increasing my LP pressure ratio, or we can say when I am increasing my overall pressure ratio for the two spool configuration, we will see our thrust, that is what is reducing. So, here you can see there is a reduction of the thrust. Okay. Now, we must realize what is the reason behind that. So, if you recall, in earlier lecture I was discussing, when we are increasing our pressure ratio, with increase of pressure ratio our curve that will be shifting towards the left hand side, and that is what is representing the reduction in thrust because of my diverging nature of pressure lines. We will see, we will discuss this in next slides. Okay. Now, the same trend we can put here, this is for say specific thrust. This specific thrust, it is nothing but it is thrust divided by m dot infinity. This m dot infinity we are not changing, that is the reason why my specific thrust and thrust they both have similar nature. Okay. Now, let us try to understand what is happening in terms of thrust specific fuel consumption. So, this is representing my thrust specific fuel consumption. So, if we look at here, it says when I am increasing my LP pressure ratio, I will be having reduction in specific fuel consumption up to certain limit. Then after it says with increase of further LP pressure ratio or overall pressure ratio, our thrust specific fuel consumption, that is what is increasing. Now, the scenario here, if we look at, it says we are having thrust specific fuel consumption, it is given by m dot f divided by thrust. So, here in this case, if we look at my change of thrust, that is what is very fast compared to my fuel consumption, and that is the reason why after certain pressure ratio I will be having rise of thrust specific fuel consumption. Okay. Now, let us try to realize the thermal efficiency, because here in this case my propulsive efficiency is 0, it is a ground condition. So, this propulsive efficiency will not be coming into the picture. Similarly, because of propulsive efficiency to be 0, overall efficiency also will be coming to be 0. So, we will be discussing about the thermal efficiency. So, here we are having thermal efficiency, that is what is coming to be in this range. This is my design condition. And here also if you look at carefully, if I am increasing my LP pressure ratio, I will be having the rise of efficiency up to certain pressure ratio, and then after there is a droop in efficiency, droop in thermal efficiency. So, if you will try to look at these two curves, specific fuel consumption and thermal efficiency, that is what is giving us the indication what is happening basically. So, here in this case, if we realize, since my fuel consumption here, that is what is changing too much, and that is what will be bringing the change in thermal efficiency. Okay. So, we can say it is not always the case that you increase your overall pressure ratio that will lead to increase the thermal efficiency. There is some limit beyond which there is no further rise of thermal efficiency is possible. It may be possible that there will be drop of thermal efficiency. So, this is what is giving us some kind of indication here. Just careful here, I am repeating again. So, here in this case we need to be very careful about the thermal efficiency variation. Now, let us try to understand, say, variation of other parameter. So, we can say my effect of HP pressure ratio, putting LP pressure ratio to be constant and turbine entry temperature to be constant. So, let us look at in line to what we have discussed earlier. Here on x axis we are putting HP compressor pressure ratio, and on y axis we are having thrust, and this axis, that is what is representing my overall pressure ratio. So, in line to what all we have discussed, basically the trend will remain same. The overall pressure ratio, when we are increasing, our thrust is going to decrease. We will see in the next slide what is the reason behind that. Now, thrust specific fuel consumption, if we look at, say, this is representing my specific thrust. This specific thrust, that is what is thrust divided by m infinity. Since my m infinity is constant, so we can say my thrust, it is following the same trend for thrust specific, say, specific thrust. Now, let us look at what is happening with the specific fuel consumption. Here also, if we look at, so what our understanding says, when we are increasing our pressure ratio, it says my specific fuel consumption, that is what is going to be decreased, because the amount of heat that required to be added, that will be decreased in this case. But after certain extent we will see, like we will be having sudden rise of specific fuel consumption. Okay. So, it is not the always case that you increase your pressure ratio, that is what will be helping you in terms of improving the specific fuel consumption also. Now, just look at what is happening with the thermal efficiency. This is representing my design point in line to what all we have discussed in earlier slide, the similar trend we are getting. Now, let us try to realize the important parameter. We have two important parameters for our cycle. One parameter I say, that is thrust specific fuel consumption, and second parameter what we say, that is what is my thermal efficiency, because we want specific fuel consumption to be lower, we want our thermal efficiency to be higher. Okay. This is what is a present requirement, but those days when we are talking about, say, 60s, 70s, during those days people, they are not bothering of specific fuel consumption, they were having major intent towards the higher thermal efficiency. Okay. So, let us look at, so this is representing the effect of my turbine entry temperature, and when we are putting our overall pressure ratio constant, that means my HPC pressure ratio and LPC pressure ratio we are putting constant. Here if you look at, when we are increasing our turbine entry temperature, it says we will be having a rise of thrust. So, this we know, when we are moving towards higher turbine entry temperature, our Joule cycle, Brayton cycle, that is what is moving towards the right hand side, and that is what will be giving higher exit velocity, and this higher exit velocity, that is what will lead to increase the thrust. Now, specific thrust, we can say it is having similar trend as our thrust. If we look at here, this is what is something interesting. Here in this case, if you look at, when we are increasing our turbine entry temperature, we can say our specific fuel consumption, that is what is going to be increased. So, we can realize here, in order to raise the temperature you need to add more amount of fuel, and that is what is in direct relation. So, say thrust specific fuel consumption is in direct relation with your mass flow rate of mass of the fuel. Now, here in this case let us look at what is happening with the efficiency. This efficiency plot is somewhat different. What it says, like here in this case, this is my design point. So, beyond that point if I will be going, my thermal efficiency is going to be reduced. This reduction in thermal efficiency is because of increase of mass of the fuel, that is what we are injecting inside. So, now the question will come, say when we are designing our 2-spool configuration engine. Suppose if I consider I have 2-spool configuration, I am having a freedom to select say pressure ratio, I have freedom to select my turbine entry temperature, I have freedom to select my say HPC pressure ratio, LPC pressure ratio, and based on that we will try to design the engine. Suppose say this is what is in line to what we have designed. Now the question is, what is your requirement? What is your target? Are you looking for increase of thermal efficiency, or are you looking for say improvement in specific fuel consumption, or you are looking for both? That means we need to optimize our results. We need to find the optimum pressure ratio, we need to find the optimum temperature. Okay, and that is where this parametric study, that is what will be coming into the picture. Okay. Now, let us try to understand this in a fundamental way. So, this is representing my ideal Joule cycle. For sake of simplicity, we are assuming this for our explanation. Here it shows the effect of pressure ratio and what is the effect of turbine entry temperature. So, that is what is very important for us. So, we have discussed first 2 plots where we have increased our overall pressure ratio and we kept our turbine entry temperature to be constant. So, here in this case let us say this is my turbine entry temperature, that I am putting constant. Now, let us try to increase this pressure. Suppose say I am increasing my pressure from 2 to 2 dash, and if I will be putting say constant pressure line, here in this case it will be intersecting my temperature line somewhere here, and if I plot it, it says my 4 dash point and 5 dash point. So, if we will try to look at here in this case, this enthalpy what I have H4 minus H5 and H4 dash minus H5 dash, we will see my H4 dash minus H5 dash will be lower. That is what is indicating my exit velocity to be lower. When I say my exit velocity is lower, we can say our thrust will be lower. Okay. At the same time, if we look at here, it says the amount of fuel required to be injected or amount of heat supply, that is what will be reduced. Say earlier it was say my H3 minus H2, here in this case, this is what will be say H3 minus H2 dash. Okay. So, my amount of heat required to be supplied, that will be reducing, and that is what will lead to improve the thermal efficiency. Now, suppose if I consider I will move further. So, if I will be moving further towards the left hand side, we will see the velocity at the exit will be reducing. At the same time, since these lines are say diverging lines, and that is the reason why there is not much variation is happening in terms of amount of heat supply, and that is what we have observed when we are moving with the increase of overall pressure ratio. Just try to recall what we were discussing, and this is what is the indication. It says like we will be having our denominator term for the thrust specific fuel consumption, that will be lower, and this is indicating my thrust specific fuel consumption, that's what will be increasing with the increase of my pressure ratio. So, do not get confused in terms of understanding. There is very important parameter. Those parameters we say they are basically overall pressure ratio and turbine entry temperature. Now, let us look at what is happening with say turbine entry temperature. Say this is what is my turbine operating temperature, and here if we look at, this is representing my enthalpy at the exit H4 minus H5. Let us try to look at, we will be increasing our temperature. So, when I am increasing my turbine entry temperature, the amount of heat supply will be H3 dash minus H2. And if this is the case, we can say our exit velocity, that is what is increasing. So, this increase of velocity, it is H4 dash minus H5 dash. Okay. So, this is indicating with increase of turbine entry temperature, we are able to increase the thrust, but at the same time amount of fuel required to be supplied, that also will be increasing, and that is what will be reflecting in terms of thrust specific fuel consumption. Let me move beyond this point. Say this is what is my point. Here in this case, if we look at, this is representing say the higher temperature or beyond higher temperature, where I will be having my thrust, that is what will be improving. But at the same time, if we look at, since this line is diverging line, my amount of heat supply required will be increasing, and that is what will be reflecting in terms of higher thrust specific fuel consumption. So, do not get confused, do not get mixed up with what all we are discussing at this moment. Just try to understand this part. Okay, I feel maybe you can make a small program, that is what will be helping you in order to find the parameters what all we are discussing, and that is what will be building your confidence. Now, let me take the next parameter, that is what is effect of mass flow rate. So, we will try to increase the mass flow rate. So, we have taken the variation here from lower mass flow rate to higher mass flow rate. It says when I am increasing my mass flow rate, my thrust, that is what is going to increase, because it is in direct correlation with the thrust. In the case of my thrust specific fuel consumption, since my amount of mass flow rate, that is what is increasing, it has not much influence on specific fuel consumption. So, this is what will be giving you some other indication we will be discussing as we go along. The next parameter what we have is in terms of the thermal efficiency. So, there is no variation of thermal efficiency that is happening with the increase of mass flow rate. Now, this mass flow rate, that is what will be used for the calculation of our exit area. So, this is what is my design condition. So, if I am increasing my mass flow rate, it says my nozzle area which is going to increase. Let me put the point here. So, in order to increase the thrust, we have different possibilities. One of the possibility, it says increase your turbine entry temperature. Second possibility, it says you increase your mass flow rate of air. Suppose if I say I am increasing my mass flow rate of the air which is going inside my engine, that means I need to have my entry diameter to be large. When I say my entry diameter which is going large, it may create the trouble in terms of installation. It will be increasing the weight of the engine, that will be increasing the drag of the engine, and that is the reason why we are putting constraint in terms of selection of entry mass flow rate. Okay. Turbine entry temperature we have already discussed with. Now, here in this case, if we look at, we have done discussion about say single spool configuration, we have done discussion about the two spool configuration, and if we look at and if we collect the information which engines are available, it says around 60 to 70% engines are single spool configuration, and remaining 30 to 40% engines are two spool configuration. So, people they found not much benefit in terms of say what is next requirement in terms of efficiency, in terms of specific fuel consumption, and that is the reason why two spool configuration, that is what has not that much popularity. So, here we are stopping with this class. I am sure you are able to understand the turbojet engine. So, in this week we have discussed about the single spool turbojet engine. We have solved the numerical for flying condition, we have done the numerical for the ground condition. Same way for the two spool configuration, we have taken the numerical for the ground condition. Now, this is what is making the initial stage. So, just understand we are presently discussing about the old engine configurations, where we are starting with say 40s, 50s and 60s. As we move along, you will be realizing how this innovation or the progress of these engines are happening, and that has happened throughout the year, and what are the new developments, what are the new requirements, and based on that what all engine developments are going on. So, here we are stopping with. Thank you very much for your kind attention. We will be discussing about the turbojet engine in further lectures. Thank you.